Hello, everyone. Welcome to the Parsons Technical Webinar Series. I'll be your host today, Jessica Bennett. Today, we're excited to have with us Mark Kluger from TRS Group presenting on thermal desorption of PFAS-impacted soil. Particularly, we're very excited to announce that as of January 2025, Parsons has acquired TRS Group. They were formed back in 2000, and they've been an industry leader in PFAS, thermal, and holistic environmental remediation. And they've cleaned up hazardous and toxic substances from soil, groundwater, and fire suppression systems for clients throughout the globe. To date, they've completed over 160 in situ thermal remediation projects and established themselves as a proven operator to treat VOCs and SVOCs, as well as PFAS, energetics, and pesticides in soil, groundwater, and bedrock. So today we'll have a presentation about TRS's thermal remediation technology and its innovative application to PFAS. Next slide, please. So just a few housekeeping items first. We'll be keeping all phone lines muted throughout the webinar to keep background noise down. If you have questions, you can enter them into the chat feature at any time. And we'll also be taking questions if you want to ask them live at the end during the Q&A session. This webinar has been approved for one professional development hour or PDH credit. If you'd like to receive a PDH certificate, there will be a link posted in the chat a few times throughout the webinar. And there will be 3 multiple choice questions that you'll have to answer in order to get credit. And those will also be posted in the chat in the event that you have any issues downloading or accessing the form during the webinar. And if you have any issues getting that form or certificates, you can request them by sending an email to the email address shown on the screen. We'll be issuing PDH certificates towards the end of the month this year, so they won't be available until probably the 27th or 28th. And finally, this technical webinar is being recorded and will be posted to the Parsons YouTube channel in the coming days. So a brief agenda for today, we'll introduce our guest speaker, Mark Kluger, followed by a core value moment. And then we'll get into the technical presentation, which is why we're all here. And we'll wrap up at the end with some questions and answers. So Mark is the Vice President of Market Solutions for TRS Group. He's been with them since 2017. And in total, he has over 40 years of experience in analytical instrumentation and subsurface characterization and remediation. He got his bachelor's in natural sciences from Johns Hopkins. And as I mentioned at the beginning, Parsons acquired TRS earlier this year in January. And with that, I will hand it off to Mark for the core value moment.
Okay, well, thank you. I appreciate the opportunity to speak. And I was instrumental in producing these slides, and I see that I've misspelled the university I went to, and this is awful. It's supposed to be Johns Hopkins University, so I apologize for that typo. As Jessica mentioned, Parsons purchased TRS just a few weeks ago, and one of the interesting things when we were meeting with the executives at Parsons is how closely our core values aligned. And it was really when we met for the first time, there's lots of discussion about the core values that you can see on your screen, and how the companies really seem to align on a people basis. So that was really very nice to see. And I'm going to talk about safety initially. TRS is super focused on safety. We are using electricity to heat up soil, both in situ and ex situ. And electricity is something that can hurt you. So not only do we have a behavioral safety program at TRS, but everybody in the company takes a cognitive function test daily before they start work. And when I say everybody, I mean everybody from the CEO on down to the people in the field doing the heavy lifting. It's a software-based program where you see a number of images. I do it my computer. I did it earlier today. Everybody does it, and I have to discern which image is slightly different, and it times me. And the first few times you take the test, you establish your own personal baseline, and then the software evaluates how well you did that morning based on your personal baseline. So we don't want people showing up to our sites without really having all their cognitive abilities or functionality. And it may not just be related to substance abuse or alcohol abuse. It could be stress in your life, a sick child or parent, what have you. So anyways, it's something that we do every day. It's an important part of our program. Again, we're super focused on safety. We've completed actually over 200 projects, three of which have been the thermal desorption of PFAS. So in today's presentation, I'll talk about the basics of thermal remediation and then talk about the projects that we did remediating PFAS-impacted soils. We're a collaborative group. We've been in business since September 2000, and we have completed every project. We 100% of the time we meet our contractual obligations. So even if it means that we're going to lose money on a project, we take our contracts seriously and stay there until we meet our obligations. And our mantra is there in the bottom. We don't want to surprise our clients. We want to do it on time and on budget. So remediation is difficult. Subsurface remediation is difficult. And this is a video that Tom Sale at Colorado State University put together. It must be more than 10 years ago, 15 years ago, perhaps. It's been a while. What we have is a sand tank with 4 clay lenses in that sand tank. And water, contaminated water, is just water that's dyed green, is going to move from left to right in the sand tank. And then we're going to have clean water, which is just dyed blue that comes through the system. And let me, I messed up. Please forgive me. I did it again. Okay, here we go. So you can see that the contaminated water or the water dyed green bypasses those clay units. And then we see each second in this video is supposed to represent a year. Clean water comes through. And look, we see contamination coming off those clay units. What we didn't see initially is although the contaminated water bypassed these clay units, that contamination diffused into the clay. And now what we're seeing is the contamination diffusing out. The rate of diffusion is based on concentration gradients. So with clean water going by the clay, we have contaminant moving out of the clay into the clean water. And this is a really difficult problem for advective flow-based solutions where we're moving fluids into the subsurface. It could be gas phase fluids, liquid phase fluids. You can't get them to go into the clay. They're going to bypass the clay. The only mechanism into and out of the clay is through diffusion, which is a very slow process. But when we're talking about years, most of the contaminant mass that's now in the matrix is in these clay units. How do you solve this problem? Well, I think there are probably 2 ways that are commonly used. And one is you can dig it up. And that's certainly a viable solution if you can dig it up, which doesn't get you out of the liability, of course. You're just transferring it from point A to point B. Or you can heat it up. And it's just as easy to heat clay and volatilize the contaminants as it is the sand units. It does not matter. And we can do this in the vadose zone. We can do it in the saturated zone. So that's the good news. The bad news is heating solutions are not terribly inexpensive. In order for TRS to do a project, it's going to cost at least $1 million. And in fact, I don't remember the last time we did a project for $1 million. I think recently it's been at least 1.3 or $1.4 million for our projects. But if it's cheaper to dig it up, that's what we would recommend. Or if you can meet your goals and objectives doing something else, bioremediation, soil vapor extraction, what have you, go at it. Thermal solutions are source zone solutions. We're applying the technology to get rid of the sources. You can use it for the down gradient plume. I just think it's a little bit pricey for that kind of application. So, typically the larger the project, the lower the per unit cost, the per cubic yard cost. And this graphic in the right perhaps doesn't indicate that, but we do get economies of scale. All right, next slide here. So I'll just go through some of the basics of applying a thermal solution. As I mentioned, it is a source zone remedy. It'll work in the down gradient plume, but again, we just don't see people applying it that much for that application. And perhaps surprisingly, the first thing that we remediate is a separate phase liquid. It says DNAPL on your screen, but it could be DNAPL or LNAPL. And I will describe why that happens or explain why that happens a little bit later in the presentation. Please keep in mind that the maximum temperature of water is its boiling point. All right, so when we're treating volatile organic compounds, we can treat that in the saturated zone, in the vadose zone. And please keep in mind also that the vadose zone has lots of water in it, right? You look out your window, you see plants growing outside. Those plants are getting their water from the vadose zone. So there's ample water in the vadose zone to support remedial efforts and so on. And I'll get into that in a little bit as well. But if we're going after higher boilers, such as PFAS or semi-volatiles, we need to get to temperatures beyond the boiling point of water. And so for that reason, we apply higher temperature thermal solutions primarily for vadose zone applications, because you're not really gaining any benefit with a technology that gets you to higher temperatures if you're in the saturated zone. You do have the option of dewatering the saturated zone, but that's not something that we would typically recommend. We just don't see our clients doing that. So for thermal remediation, we can apply these technologies and reduce contaminant levels in the saturated and unsaturated zones for the volatiles, but for the semi-volatiles and things where we're going to higher temperatures, that's going to be primarily a vadose zone or an ex situ application. And we are a turnkey contractor. The purpose of applying a thermal solution is to put the contaminant into the vapor phase. So you have sorbed and liquid phase contaminants in the subsurface, and we're going to volatilize them and then capture those vapors and treat them at the surface. This is not a destruction methodology. Actually, fundamentally, it's a concentration method, right? We're getting it off the soil, out of the groundwater, bringing those contaminants up into the vadose zone, capture them in the vadose zone, and then treat them at the surface. This remedy, these thermal remedies are quite fast. They typically turn the switch on, turn the switch off is a 3 to 6 month process. From notice to proceed to demobbing, we have permitting, we have construction, design, engineering, all these things. Our projects usually go anywhere from 11 to 18 months, but the actual heating period is much less than that. And typically we're looking at mass removal rates in excess of 99%. In the case of PFAS, we're targeting at least 99.998%. So, you call us up and you say, we've got a project. Our assumption is that you want at least 99% of that contaminant gone. So there are two types of technologies, thermal technologies, that are widely used. These two, conduction heating and resistance heating, account for more than 99% of the applications. We also can generate steam at the surface and inject that steam, but steam's a fluid, right? And fluids, as you saw from that video, go to the high K units. And it's much more efficient to treat your contaminant by generating the steam in situ. That said, occasionally we'll get an inquiry about injecting steam into the subsurface. So these two, as I mentioned, are the vast majority of applications. And you can see from this slide that conduction heating will handle a much larger range of contaminants with different range of boiling points than resistance heating. So, I think a legitimate question is if resistance heating is just working on a subset of these things, why not just use conduction heating all the time? And the answer is that if resistance heating will work at your site, and you can see, the constituents there where it's appropriate, it's going to be less money than applying conduction heating. So, we would like to provide a solution that meets our clients' needs at the lowest possible cost. And for that reason, we will apply resistance heating for chlorinated ethenes and so on. It doesn't mean that the technology is less effective. That earlier slide, I didn't go through it much, but here, this is a project outside of Washington, D.C. This was a resistance heating site. Again, it doesn't mean it's less effective, right? 99.995% removal. It just means that resistance heating is just going to work on a subset of the contaminants. Again, keep in mind that the maximum temperature of water is its boiling point. All right. So, and I'll get into why that's important with resistance heating in a moment. So if we compare the technologies here, with resistance heating, our maximum temperature is the boiling point of water. And that's because we have to have water in the matrix to conduct electricity. So I'm going to jump ahead. Probably should have these slides in a different order, but this is what a subsurface thermal remediation looks like, whether we're doing conduction heating or resistance heating. Municipal power, which is like what, around 12, 13,000 volts, goes into a power control unit. We call it a PCU, power control unit, steps down that voltage, and we put that electricity into the subsurface. In the case of resistance heating, we are not heating these pipes. In fact, we call them electrodes. We don't call them heaters. And the electrodes are the same temperature as the formation. The formation completes the circuit among the electrodes. The formation is the resistor. Resistors get warm, and in this case, we can get to the boiling point of water. The formation must have water in it to conduct electricity among the electrodes. So again, people say, oh, well, it's not going to work in the vadozone. No, but there's ample water in the vadozone to conduct electricity. But because we have to have water in the matrix to conduct electricity, the maximum temperature we can achieve is the boiling point of water. With conduction heating, it pretty much looks exactly the same. However, in this case, we're heating the pipes. And we call these pipes heaters or heater wells. And we heat these pipes to about 800 degrees Celsius. And the heat front propagates radially away from these individual pipes. And we can achieve average temperatures well above 400 degrees C in the formation, but that's going to be in the vadozone, right? Because again, maximum temperature of water is its boiling point. Keep in mind that earth materials are really good thermal insulators. So the heat front that propagates away from these pipes, its rate of propagation is about 3/4 of an inch a day. And that varies somewhat based on the soil type or rock type that you have, but pretty much it's pretty slow. With resistance heating, it's more uniform temperature increase because again, the formation is acting as the resistor and it's heated more uniformly. So those are the two main differences. But again, the application or the intent is to take these liquid and sorbed contaminants and put them in the vapor phase, collect the vapors in the vadozone, and then treat them at the surface. So if we compare these technologies, we see that with resistance heating, we can only get to the boiling point of water. I just explained why that was. And in the Vado zone, we can get to very high temperatures with conduction heating. But again, in the saturated zone, you'll lose that benefit of those higher temperatures. Resistance heating is um, more energy efficient. We can put our electrodes further apart than we can with our heaters in conduction heating. Resistance heating is faster. We can get to boiling temperatures in about 2 months and a little bit longer with conduction heating. There are not that many companies out there that provide these technologies. Three for resistance heating, four for conduction. TRS is a company that does both of them. We initially did resistance heating back in early 2000. And about 7 years ago or so, we started doing conduction heating, and all of our PFAS projects and to date have been through conduction heating. There's no possibility of desiccation with resistance heating because we have to have water in the matrix to conduct electricity. But with conduction heating, we can desiccate the Vado zone. So that's something that we have to really pay attention to when we have sensitive infrastructure at the surface. Roads, buildings, railroad tracks, these kinds of things. We just need to be aware of it and design accordingly. And with resistance heating, we're not going to have any impacts to the organic carbon in the matrix, but that's not the case with conduction heating in the Vado zone. We are going to essentially break down that organic carbon. And again, that's something that we have to pay attention to. So I'm going to take a break right now. Jessica, are there any questions to date or up to this time?
No, it doesn't look like we have any questions yet. But anyone can please feel free to enter your questions in the chat, or you can wait until the end and ask them live if you'd like. So I think we can keep going at this point, though.
Excuse me. Okay, I'll do so then. Okay, so I mentioned that we are getting to the boiling point of water. So what is boiling? Boiling is when the vapor pressure of the liquid equals ambient pressure. So, if I had a glass of water on my desk and I'm at pretty much sea level, I'm in Delaware, and you would ask me what's the boiling point of water, I would tell you, that glass of water is going to boil at about 100 degrees Celsius. If I had the pleasure of being in Vail, Colorado, the boiling point would be less because the ambient pressure, atmospheric pressure would be less due to the, elevation at Vail. If we had 20 feet of hydrostatic head above the water, then the boiling point would be higher than 100 degrees C. So I've been saying all along that we're going to the boiling point of water. I haven't said that we're going 100 degrees C. So it's really more accurate to say we're going to the boiling point. We are creating steam at the subsurface, right? We're going to the boiling point of water. And that steam is used as a carrier gas to carry the volatilized contaminants up into the Vado zone. So what happens when you have a separate phase liquid, let's say a chlorinated ethene, for example, PCE, TCE? When that separate phase liquid comes in contact with water, it forms something called an azeotrope. And the boiling point of the azeotrope is the summation of the vapor pressures of the two different liquids, in this case, water and PCE. And because it's a summation, that it's additive, the boiling point of the azeotrope, by definition, has to be lower than the boiling point of water. So this is a really nice feature for us because the first thing that we remediate with a thermal solution is the separate phase liquid because it boils at a lower temperature than the water. it presumes that we have to have contact with water, but we're going to have contact with water in the subsurface, either water or moisture. And this is explained by Dalton's law of partial pressures. You can, after later on, you can look this stuff up in Wikipedia, what have you, for a more thorough explanation. But it's a great feature of thermal solutions that the first thing that we remediate is the separate phase liquid. So here's just an example. We take a compound like dichlorobenzene, 1,2-DCB. It boils just under 180 degrees at 1 atmosphere. But in the presence of water, it boils at 98 degrees C. And what you see here in this in this photo, this gas bubble right here is water vapor in 1,2-DCB. So again, the first thing we remediate is a separate phase liquid. And notice the water itself isn't boiling. We just see the NAPL, the DNAPL, that azeotrope is boiling. Okay, so you reach out to us and say, okay, we've got this site. Does a thermal solution make sense? And we would ask for a bunch of information um, and make a decision on which technology is most appropriate for your site, conduction heating or resistance heating. And essentially, we're looking at the heat losses in the system, the constituents of concern, groundwater velocity, all these typical kinds of information that you already have. And we're going to do heat loss calculations and recommend spacing of our heaters or electrodes, how long we're going to run it, how much energy we're going to use, and come back to you with our technical approach and our pricing. And by the way, the pricing that I provided much earlier in the presentation is all inclusive. It's electricity, it's drilling, all the energy that you're going to use, our design, permitting, yada, yada, yada. It's everything. Typically, it does not include the consulting time, but everything else is included in our pricing model. And so there are two things that we look at primarily when we're designing a site, and they have to do with power and energy densities. So we have to put sufficient power into the formation to overcome the heat losses, and power times time is energy. So the amount of time that we spend on the site, once again, overcoming those heat losses, then determines the amount of mass removal that we're going to get. So these are two important parameters for us. So this graph that you see to the right, it's a semi-log plot on the y-axis. We're showing the percentage of contaminant that remains. And on the x-axis is the energy density, power times time divided by the cubic yards or cubic meters, what have you. So if we look at 0.1, that indicates that we've gotten rid of 99.9% of the PCE or TCE in this case. And you can see that the energy density required to get to that removal efficiency is greater for PCE than it is for TCE. Why? PCE is less volatile. That's primarily the reason. It could be Henry's law partitioning issues as well. But we do this on every one of our projects. And one of the constituents of concern will be what we call the driving constituent, or the constituent that we have to design to meet our goals and objectives. And in the case of PFAS, because we need to get to much higher temperatures, the energy density will be much higher. So perhaps this middle bullet is not intuitive, right? With conduction heating, we can get to higher temperatures than resistance heating, but we can input more power per unit time, per length of electrode than we can put in power for length of heater. And that's because, as I mentioned earlier, earth materials are really good thermal insulators. If we overpower our heaters, we'll melt them. The formation won't be able to take the heat fast enough. So another reason why resistance heating tends to be less money than conduction heating, because we can input power more quickly. We do work in rock, and I think that comes as a surprise to folks. This particular site's about 150 miles north of where I live. Um, in less than 3 months, we removed 99.9% of the contaminant in the bulk matrix, not just in the fractures, but in the primary porosity as well. And we've done, I think we're up to something like 19 sites now where we've remediated rock matrices. So you have DNAPL in rock. It's the first thing that goes away. These are really very powerful technologies. The Flex heater is our brand name for conduction heating, and this is what we're going to be using for PFAS remediation. This is what we're showing here is a Superfund site in northern New Jersey. On the right side of that wall is a manufacturing facility that we did not have access to. And what you see in the foreground, those gray boxes, each of these individual gray boxes is voltage controlled to a individual heater. So if you were going to shake somebody's hand, your hand would sort of be in a vertical orientation, and each finger would be at a different angle. And that's what we have here. Each of these heater pipes are at different angles, and we call a row of these heater pipes, we refer to it as a heater fan. And we had 14 parallel heater fans at this particular site. This was the most complex drilling site that we've ever done, and it was a huge success. 5 miles of drilling, heaters were as long as 230 feet, limited space. We routed stuff on the roof. It was really a very interesting project, and we did all this during the right in the middle of COVID. It was quite a project. And this is what perhaps a more typical conduction heating site would look like. This is in the Pacific Northwest. Again, each of these individual gray boxes is voltage control for these heaters. In the foreground here, we see our PCU, our power control unit, which again is delivering power to each of these voltage control boxes, and then we're heating up the subsurface. We also see aerated concrete here, so this acts as a thermal barrier. We were heating very close to the surface, and our goals here, we needed to get to high temperatures for vadosone impacts. Okay, let's talk about PFAS. So you saw this slide earlier, or similar slide earlier, and we took a look at these various PFAS compounds, and we can see the vast majority boil off below 300 degrees C. Now, this is just a small smattering, right? We have tens of thousands of PFAS compounds out there. Typically, the smaller the compound, the shorter carbon length chain, the more volatile it's going to be. Not all the time, but that's generally the case. And so again, although we're just showing a small subset of PFAS compounds, again, the vast majority boil at less than 300 degrees C. So we said, oh, this is interesting. With conduction heating, we can get to these temperatures, and we don't want to waste anybody's money. So let's run an experiment at 300 C and see what kind of removal efficiency we get. And it was rather disappointing. We just did not see the removal that we had expected. So we hypothesized that because of these long carbon chain compounds, and we have functional groups as the heads of these compounds, that we're going to have both van der Waals forces and electrostatic forces with the organic carbon in the matrix. So the thought was, well, what temperature can we break down that organic carbon to release the PFAS? So prior to our discovery, the thought was the literature indicated that you had to get to at least 650 degrees Celsius to volatilize these compounds. But lo and behold, we could hold the temperature for 350 to 400 degrees C and get excellent removal. We just needed to hold those temperatures long enough to break down the organic carbon. So nowadays for PFAS, we are targeting 400 degrees C for what you see is practically 5 nines mass removal. And we were able to patent this. So we have a patent for the thermal conduction, thermal desorption of PFAS from soil using thermal conduction heating. We have an awesome patent attorney. Turns out it was my wife. Joan used to practice intellectual property law, and she subsequently retired, but she did all that patent work for us. So we've got 3 completed projects, as I mentioned earlier in this presentation. 2 are ex situ, 1 was in situ, and 2 are in Alaska. That J-Bear site is in Anchorage. Eielson is in Fairbanks. Beale Air Force Base is about 50 miles north of Sacramento in California. These were all funded by ESTCP. It's an acronym. I can never remember what it stands for, but it's a Department of Defense funding mechanism, research funding mechanism. DoD has something called CERTIP and then ESTCP. CERTIP is more laboratory-based research, and ESTCP is taking that research and doing pilot studies in the field. So each of these were funded by ESTCP. The first 2, as you can see, the treatment volumes were rather small, which was great for us. We got to learn some stuff, and then we applied it at J-Bear, Joint Base Elmendorf Richardson. It's easier to say J-Bear, for a 2,000 cubic yard soil pile. The first 2 we used essentially vertical heaters. At J-Bear, we had horizontal heaters. I believe they were over 100 feet long. And you can see that the total length, huge difference between those first 2 sites and the work that we did at J-Bear. All right. So this is what it looked like at Eielson. Eielson there's a lot of military construction going on at this site in Fairbanks. They have lots of soil piles. They gave us one of the smaller piles and they said, go at it. And you can see these individual heaters. Some are sort of at strange little angles, and that's because the soil pile has strange angles. So we wanted to make sure that we were treating the entire soil pile and thermal insulation on top, and so on. And we reached our goals and objectives here. I believe our goal here was just to get to 350 degrees Celsius, but again, we had great mass removal. This is the work that we did at Beale. This is an in situ project. So you remember that site in the Pacific Northwest sort of looks similar. But this is much smaller. Again, these individual gray boxes for voltage control. You can see the aerated concrete. We were treating here from grade to 13 feet below grade. If we're going to do in situ work, we need to be sufficiently above the Vado zone, right? The maximum temperature of water is its boiling point. When we start creating steam, that steam's right around 100 degrees Celsius. That steam will cool down our site, our treatment volume. It's not intuitive, but you don't think of steam as being a cooling agent, but in this case, it would be. So the depth to water at Beale, I think it was something like 55 feet below grade. Of course, when we did this work, it was from grade to 13 feet, so we're certainly well above the Vado zones, not to create steam from the Vado zone. But we had record rainfall when we were doing this work. There's a purged aquifer. Water flowed in, I believe, from the east side of the site. So on the downgradient side, we got to our temperatures, but because that cooler water was coming in, we could never get to 400 degrees C on the eastern side. We still got some removal, but not what we had hoped for. But we took those same samples and then heated them up to 400 degrees C and removed all the PFAS, again, down to non-detect levels. So it was just an interesting lesson for us. And then the work that we did at J-Bear, this again, it's in Anchorage, and we have some cooler weather there in Alaska. We built this structure to keep the elements off the soil pile. And this was unlike Eielson, where we were just given a soil pile and said heat it up. Here we were able to engineer a soil pile, which was pretty interesting. Um, so you can see here at the very bottom that we have these horizontal pipes, these heaters. So we were actually able to separate the soil pile from the earth beneath it, from the soil beneath it. And again, you can see this insulative layer to protect or to isolate that thermal pile from the ground. So there are all sorts of advantages with building an engineered soil pile. We can size it for optimal thermal properties. If the site's large enough, we can have multiple piles. We can move dirt into one, take it out, put it back in. Not that same dirt, but um, other soil that's impacted. Like all of our systems, we build in vapor capture and treatment. In my estimation, what's so nice about this is how simple it is. We do not care what's in that soil pile. We don't care about the grain size of the soil. You can have boulders in it. You can have construction debris. You could have roadway materials. None of it matters. We put these heaters into that pile, flip the switch, and we're going to get to really high temperatures. Um, there's been some other methods that people have applied, but those, not the conduction heating, other heating methodologies. And if people are interested, I'm happy to chat with them about it. But they're much more complex and require much more attention to what's in the pile and moving those soils around. So there's great advantage to an engineered soil pile. And then here's a photo. We're now starting to build that soil pile. Again, you can see these horizontal heaters. And again, I believe they're all over 100 feet long. This is a cross section of what a heater looks like. And then you can see when we flip the switch, it gets pretty hot. So the way this method works is we put these pipes in either vertically or horizontally into your treatment volume. And then we put a wire inside that pipe, heat that wire, and the energy transfer, glows red. The energy transfer from that wire to the steel pipe is through infrared radiation. This is the same way your toaster oven works. It's infrared heating of your slice of bread, if you will. That wire gets extraordinarily hot. We can get the steel pipe again to above 800 degrees Celsius, and then the transfer of energy from the pipe to the soil is through conduction. And that's why we call it conduction heating or thermal conduction heating. And we can make these pipes as long as we want. And you see there's ceramic spacers. We don't want that wire to hit the pipe because it'll short out. So again, this is a patented design of our thermal conduction heating solution. Again, another photo of building the soil pile. And at the end of the day, we had 2,000 cubic yards of soil here. This is sort of like a rubberized silicon, easy for us to manipulate and has great thermal properties. And we're able to build in sampling, a sampling system, if you will, to allow us to collect soil samples for subsequent analysis. And if we take a look at what our goals were and what the results were, you can see we had a contractual goal of getting to an average temperature of 400 degrees C with no sensor below 350. And we put our temperature sensors in the coolest part of the pile. So I mentioned we had horizontal heaters and they're layered and they're offset. So you're essentially creating equilateral triangles, if you will, for these heaters that, of course, it's three-dimensional. And so we put our temperature sensors at the centroid of those equilateral triangles. And we crushed it. Instead of, our goal was to 400 degrees C, but you can see we had above 630 as an average with no sensor below 440. Frankly, this was over designed. I think the reason that we were able to achieve and we did this in 89 days, by the way, once we flipped the switch. The reason that we were so energy efficient was because we were able to isolate that soil pile from the ground beneath it. The lab that was contracted by ESTCP used EPA method 1633, which includes 40 analytes. So 30 samples, 40 analytes that's 1,200, I guess, separate analyses. We were non-detect on 1198, I believe, and the other two were just slight ticks. So we were below EPA RSLs for all samples. Again, we just crushed it. This is a very efficient way of removing PFAS from soil. For those folks who are doing federal work, again, the funding came through the Department of Defense's ESTCP, but the contract was managed by something called the Defense Innovation Unit, DIU. And DIU is about to issue to us something that they call a success memo, which will allow any federal agency, not just DOD, any federal agency to sole source this work to TRS. And I know it sounds crazy. This is not through the FAR, it's through something called the Other Transactional Authority, OTA. I don't really speak contracting, but the folks at DIU do. So again, if there are any federal people on this call and interested in more information, I can put you in touch with the folks at DIU who can explain. These folks can explain to you how this contracting works. It's not a source of money. It's just another way of doing contracting to get us to get essentially to ease the procurement process. It makes it much faster. Excuse me. So if you hire TRS, you get rainbows at your site. And typically we're talking about more than 99% removal of these contaminants. In the case of PFAS, we're targeting higher removal efficiencies. Safety comes first. We don't want anybody getting hurt. And I talked about our safety program. We've been in business since September 2000, completed hundreds of 200 plus projects, and as I mentioned, 3 of which have been PFAS. And again, our goal here is to essentially get to non-detect for these PFAS compounds. And so my contact information is here. And I think that pretty much does it. I'll take some questions.
Yeah, thank you so much, Mark. That was a great presentation on thermal remediation and how it's being applied for PFAS, which it seems like is being found at almost every site these days. If there's any questions, you can enter them into the chat at any time, or you can raise your hand and ask it live. Looks like we've already got a good number in the chat so far. So we'll start off with the first one. Does the soil matrix being backfilled? Sorry, I need to reread this question. I'm going to do my best with what this question is asking for, and if the person who submitted it, if it doesn't answer, let me know. So does the soil matrix being backfilled or regraded impact the heat loss calculations?
Yes, because, well, as I mentioned earlier, soil is a really good thermal insulator, and the rate of propagation of that heat front it is based on something called the thermal diffusivity. That's the parameter that we're measuring. But the whole range of thermal diffusivity is a factor of 4, regardless of the types of soil that we're dealing with. Compare that to hydraulic conductivity at a site where we're looking at what, 7, 8 orders of magnitude is not unusual. So essentially, earth materials transmit or propagate that heat front rather uniformly. So if, yeah, with soil that's not compacted, it might slow it down a little bit. At this particular site, I believe the spacing between the heaters was about 6 feet, maybe a little bit less. So that's why we were able to get to temperature so quickly. Again, it was engineered with that insulation at the bottom, but we had a high density, if you will, of heaters in that soil pile. So we will account that, we're going to be asking you folks questions about how quickly you want this done. If time's not of the essence, it may make sense to space the heaters a little further apart, but we can have that discussion. But the answer to your question is yes, the moving the soil around will affect the rate of propagation of that heat front.
Thanks, Mark. Next question is, what concerns are there for the microbiomes that are affected by these methods, and does a soil require microbe reseeding afterward?
Yeah, so those poor bugs are not going to do well. If we're talking about PFAS, where we're going up to these, very high temperatures, we're going to kill the bugs. We're going to break down the organic carbon. So if your intent is to reuse that soil to support plant growth, it would certainly need to be amended. But that's an easy and inexpensive thing to do. You add some mulch, you put in some fertilizer, and we've seen the soil come back. The soil will support growth thereafter. But if you do not amend it, it will not. So it does require amendments.
Okay, next question is, in highly fractured rock, are there similar concerns as with fracking?
I'm not sure I understand that question. Well, let me rephrase that. I'm sure I don't understand the question. So, I'm,
Okay, well, maybe the submitter of that question can maybe provide some clarification in the chat, and we can ask a follow-up question.
yeah. So something I learned in college many years ago is if you don't understand the question, answer what you do understand, and maybe you'll get some partial credit. So, when we're heating up rock, we're heating we just don't want to heat the secondary porosity, the fractures. We want to heat the bulk matrix. Now, in a what I call a cooked rock system, metamorphic rock or granitic system, the primary porosity is, very, very low. So all your contaminant mass is in the secondary porosity. Um, Typically with a cooked rock system, the electrical resistivity of that rock is very high. With resistance heating, which is what we prefer using if we can, because reasons I discussed earlier, the resistivity that we need is between 5 and 500 ohm meters. You'll have higher resistivity in a granitic system. And in that case, we'd use conduction heating, and it's easy for us to move. That heat front will propagate through that granitic system pretty much at the same rate, 3/4 of an inch a day. With with rock that has relatively high primary porosity, let's say a sedimentary system, we can heat that bulk matrix with either conduction heating or resistance heating. So typically we'll ask our clients to send us a core of the rock. We'll run a resistivity test, and if resistance heating works for the constituents of concern, we'll choose resistance heating. I hope that answers the question. If it doesn't, please, re-ask the question.
Okay, next question is, how is the resulting soil gas managed?
So we co-locate vapor extraction wells with each of our electrodes or heaters. And, if you recall from the presentation, the spacing is from, 6 to 20 feet. We have very aggressive vapor capture, whether it's in situ or ex situ. And if we're doing work under, buildings and so on, typically the consulting engineers will do indoor air monitoring on a real-time basis, or occasionally go out and take samples. So it's something we're certainly aware of and concerned with, but we just do not see fugitive emissions with our systems. It doesn't mean you shouldn't monitor. We get monitoring's important, but we have very robust vapor capture.
So there's a couple of related questions to that. So can you describe how the efficiency of PFAS recovery is measured, and is there a way to verify that it's not lost to the atmosphere, particularly for in situ applications?
Yeah, so a mass balance is the holy grail. Everybody wants a mass balance, and part of the funding from ESTCP on those three PFAS projects required that we look at a mass balance. So we're not the analytical chemists. We work closely for all three of those projects with Brown University. There's a professor there, Kurt Pinnell, that we work with. And I can put folks in touch with Kurt, regarding the mass balance. We were able to show there is going to be some transformation of the PFAS in the vapor phase to other compounds. Mass balance is a hard thing to prove, but it was part of our obligations under the contract. So yeah, we know what the before and after concentrations in the soil. That's easy, right? But let's get a mass balance. That's what everybody wants. So yeah, so there was lots of attention um, on that issue. And again, I can put anybody in touch with Kurt if you want to talk with him directly about the mass balance.
So we do a follow-up about the fractured rock question. Regarding the risk of local quote unquote earthquakes or the risk of steam fracturing the rock.
Huh. Well, I would say that there's no risk of earthquakes. The work that we do is near surface. We're not going down to the depths associated with earthquakes. Um, Regarding that, there's not a theoretical limitation on how deep we can do this work. But of course, it gets expensive. The more you're drilling, the deeper you go. Um, but steam fracturing the rock, um, I'm not sure that that would be a bad thing. I've not heard of that before, but when the volumetric change from water to steam is significant. It's 1,600 times. So perhaps there's some microfracturing going on, but we're trying to get the contaminant mass out of that bulk matrix anyway. So if in fact there were some microfracturing, that's probably not a bad thing. But I don't have a definitive answer for that question. I just don't know the answer.
Okay, next question is, are there any co-contaminants with PFAS that would pose challenges for thermal remediation?
I think the short answer is no. There could be stuff there that would be difficult for us. Our target temperature is 400 degrees C, so there are not that many organic compounds that I would see as co-contaminants that would boil at temperatures above that. It could be, but certainly if there are any metals that you have interest in removing, a thermal solution is not the way to do that, right? We're not getting to temperatures where we're going to volatilize the vast majority of metals. We are getting to temperatures where we'll volatilize mercury, um, but that's the only one that comes to mind. The
Okay.
only metal that comes to mind.
Yeah, and I'm sure it's all information that you would gather for a potential project up front to make sure you can achieve the goals of the project.
Yeah, right. So
Uh,
typically what happens when we're asked to look at a site is um, our business development people, I manage that group, can give you ballpark pricing fairly readily. It just ask a few questions, treatment volume, constituents of concern. We can come back with a ballpark price. When I say ballpark, plus or minus 50%, something like that, pretty wide range. If that ends up being in the realm of possibility, it makes sense for your site. the next level is filling out our site evaluation form. And we're going to want to see the conceptual site model, all the kinds of information that you're collecting when you're considering various remedies for your project. And that goes to our engineering group, and a week or two later, we come back with pricing. It's pretty darn accurate. I would say, -5 plus 20%, something like that. And if that seems reasonable after a few discussions, you say, okay, you folks want a price that the TRS is willing to sign a contract on, then we want to visit the site and do a little bit more research. And typical time for us to give you a real proposal that we'll live with is anywhere from 3 to 6 weeks, depending on the project.
Okay, so I know we've got a couple more questions, it looks like, but we're up against the end. So I want to just get to our last couple of slides. If anyone has any other questions you want to follow up with Mark, feel free to reach out to him at his contact information on this slide. So our next webinar will be on March 12th on California Dreaming, a look at current and future orphan well liabilities. That will be presented by Kyle Metz at the same time, 12:30 to 1:30 p.m. Eastern. A link to the PDH form for credit has been posted in the chat several times during the webinar. If you had any issues accessing that and want to get a PDH certificate, you can reach out to us. And if you missed anything with the webinar today, you can check out our YouTube channel, and the recording will be posted in the next few days. Thank you to everyone who joined us for today's webinar, and we really hope to see you again in March.
Thanks, everybody.